Hello everyone. In this video we're basically going to look at dual active bridge and the sequences involved in the switching operation of a DAB or dual active bridge converter. The converter shown in the diagram figure here is basically a bidirectional dual active bridge. Ignore this one first. That's basically a bidirectional dual active bridge converter, simply meaning that power can flow V1 from V1 this side. Power can flow from V1 to V2 and then V1 to V2, and then power can flow from V2 back to V1 using some kind of phase shift. Okay, so in a single phase dual active bridge, the primary and the secondary bridge are controlled simultaneously. So all switches operate at 50% duty cycle. That simply means that the diagonal switches turn on or off together so that the output of each bridge is a square wave. So basically the switching sequence of the converter will be explained in this video. So the switching sequence is divided into 4 intervals. We're going to look at, let's say this is interval number 1. So during this interval, the inductor current waveform in this case is both positive and negative. So when the inductor current is positive, the current flows this way. It comes through Q1, which is the switch number 1. It goes this way through the inductor. It comes all the way to the secondary side, and then it comes down to Q6. It goes this way. It goes to V2. From V2 it comes to Q7, and then it goes back this way. It goes back this way. Okay, so this is how the current flows. So the current, the direction of the current in this case is determined by the direction of the inductor current. So this is the inductor current in this case. So this is how the current flows in the first interval, and this is the positive, the current flow. And what happens to the negative current flow? In this case, when it comes to the negative current flow, the current flows from this side towards this side. So it comes this way to Q1. It goes this way again to the positive polarity of the DC source, and then it goes to the negative, comes all the way to Q4, go all the way this way, go up to Q7, comes this way, and then goes this way again. So it's basically like the opposite of the positive current waveform. So that's basically what happened in the first interval of the switching of a DAB. So in this case now we can say that the current, the inductor current, the change in the inductor current will be equals to something like V1, which is the primary voltage, plus V2, which is the secondary voltage, and then divided by the value of the inductor. So that's basically what happened in the first interval when it comes to the switching cycle of dual active bridge converter. Now during this second interval, the inductor current is positive. So the voltage across the transformer primary is positive and is equal to V1, and the voltage across the secondary winding is positive and is equal to V2. Hence the difference of these two voltage appears across the leakage inductor, and the slope of the rising current during this interval can be calculated using the change in the current. So basically when you want to calculate the inductor current in this case is equals to di on dt is equals to V1 minus V2 divided by the inductor. So that's the equation that we can use to find the change in the current with respect to some kind of time. Now let's look at the direction of the current in this regard. So what happened is during this cycle, because we have only the positive inductor current, the current comes this way. Okay, the current comes this way. The current goes through Q1, then it goes this way through the inductor. Okay, it goes to the other side, it goes out this way to Q5. Okay, and then it goes this way, it comes down this way, comes down this way, go through Q8, then it comes this way, it goes through Q4, comes this way, and then it comes this way. So this is the direction of the current in the second interval when the switch of the secondary side is changed from Q5 and Q6 and Q7 to Q5 and Q8. So the direction of the current is positive, and that's the flow of the current in the DAB. So the bidirectional movement of the current can basically be explained in terms of the inductor current in this regard. So when the inductor current is positive, it simply means the current moves this way. When the inductor current is negative, it simply means that the current direction is this way. Okay, in this positive cycle, we know that Vp in this case is equals to the V1. Okay, and then Vs in this case is equals to the V2. So that's how it works. So during the third interval, the inductor current starts ramping down from the positive peak to the negative value. In this interval, the voltage across the primary is negative V1. Okay? So this voltage is now negative V1. And the voltage across the secondary is V2. Okay? So this one is equals to this one. That's the secondary voltage is equals to the V2 voltage here. So the difference of this voltage, which is negative V1 minus V2, appears across the inductor here. Okay, so hence the current ramps down with a negative slope. So if you want to find the current across the inductor, it should be something like di on dt is equals to V1 plus V2 on L. Okay, so that's how we find the inductor current. Okay, so during this interval, switch Q5, this one, and Q8, which is this one, continues to remain turned on. Okay, but as the voltage across the primary side is negative V1, this one, when it becomes negative V1, okay, switches Q2, which is this one, and this one, Q2 and Q3, okay, turns on to conduct current. So the conduction of both direction of the current is like IL, which is greater than 0, and IL, which is less than 0, can best be explained in this case. So what happens is the current, let me use the eraser first, erase these ones. So what happened in this case is that the current flows this way. Okay, the current flows down this way. Okay, it comes this way, it goes through Q2, goes up this way, it comes this way through the inductor current, it goes this way through Q5, go all the way through, so it comes down this way, comes on back to Q8, then it comes up this way, goes this way, all the way here, goes up to Q3, and then it goes this way. So the direction of the inductor current in this case is like this. Okay, therefore when the current goes this way, we know that this is a positive inductor current. So this one, in this case, this one is the positive inductor current. Okay, so what about the negative inductor current? Okay, so in this case, for the negative inductor current, let's say the negative inductor current, let's use this one. So what happens with the negative inductor current is that the current comes this way, go down to Q3, all the way down, goes this way, comes down all the way to Q8, goes down this way, go up to Q5, comes this way, and then it goes all the way here, down to Q2, and then it goes this way. So this is basically the movement of the current in interval 3. Okay, so that is the negative IL and this is the positive IL. So one very important thing is to look at the direction of the inductor current. So when the inductor current moves from the secondary towards the primary side, we have negative. Okay, when it moves from the primary towards the secondary side, we have a positive inductor current. Okay, so the last one is during the fourth interval, the inductor current continues to be negative. During this interval, the voltage across the primary is negative V1. So during this interval, the voltage across this one is negative. Okay. And the voltage across the secondary is also negative. This one, the voltage across this point is negative. Okay. The difference in this voltage, which is negative V1 plus V2, appears across the inductor. Okay, hence the current ramps down with a negative slope. And we can describe this by using our equation. Change in current over some given time is equals to negative V1, which is the primary, V2, which is the secondary, divided by the value of the inductor. So during this interval, switch Q2, which is this one, and switch Q3, which is this one, continues to remain turned on. But as the voltage across the secondary side, which is this side, okay, is now negative V2 or negative Vs, switches Q6, which is this one, Q6 and Q7, turn on to conduct. So in this case, let me use another one. Let's use a purple. In this case, the current from the primary side comes this way. It goes down to Q3. It comes this way, goes all the way up to this way, goes up to Q7 to the V2 of this voltage source on the secondary side, can be a load or so, and it comes back to Q6, and then the current is fed back as a bidirectional to the primary side, so it goes around this way. So the direction of the current is this way. Okay, direction of the current is this way. Sorry, this way. Okay, so this is the last interval. Okay, that is when the inductor current is negative, or it remains negative. In this case, we use this equation here to find the change in current across the inductor. That's a very important thing, because basing on this one, it gives us the direction of the current flow in the DAB circuit. Okay, thank you for watching. And this is basically the 4 intervals, or the 4 switching intervals of a DAB bidirectional converter that is used. And further, the next video we will look at the 0 voltage switching of the different components, such as the capacitor here and the diode, and how they are involved in 0 voltage switching. It's a common phenomena, it's a common concept that is used in our power electronics, and mostly in DAB, to cater for switching patterns and to avoid losses when we shift from one switching cycle to another switching cycle, or from one interval to another interval. If you still do not understand what I mean by interval 1, interval 2, interval 3, and interval 4, basing on what we have covered, this is what it simply means. Interval simply means the change in the current, or the inductor current, when the voltage, the primary side and the secondary side voltage, are controlled by the switch's waveform. So if we have, for example, this is my voltage. Okay, this is my voltage. Let's say this is my primary voltage. Okay, by some 50% duty cycle, so the off state will be equal to the on state. Okay, and then let's say, let's use another color here. This is my secondary voltage. It will be spaced by some kind of phase shift. Okay, it will come this way. It will go this way, so 50% duty cycle. So we should have something like this. So that's my voltage. Okay, so what will be the inductor current looks like? Okay, let's see the inductor current. This is phase shift, so it will be like theta something. And we have, let's say this is the first interval. Okay, let's say this is the second interval. Okay, let's say this is the third interval. Okay, and this one is the last 4 interval. So we're going to look at the current changes, the inductor current changes along these 4 intervals when we look at the single cycle switching of a DAB bidirectional second. So what happens to the inductor current is this. Okay, so let's say this is the inductor current. So in this case, as the voltage increases up this way, the inductor current will start at some value somewhere here, and then it will come up this way. Okay, it will stop here. As the voltage goes this way, we would have some slight increase in the value of the current up this way. Okay, it will reach this point here. Okay, it will reach this point here, this point here. Okay, that's another point here, and then the current will drop down again down this way. That reaches some point here. That's when we have V2 changing from positive to negative. Okay, and then it will further drop down this way. Okay, once it reaches this point here, it will increases up again. Okay, and then the same process repeats. Okay, it will come down this way, come further down this way, then it will go up this way. Okay, so that's what normally happens. So this is my interval 1, this is my interval 2, this is my interval 3, and this is 4. Okay, so now what happens between these points here? Okay, between this point here, between this point here, between this point here, what happens, okay? When the timing here reaches t is equals to some kind of time, okay, let's say some kind of time, what happens here is a phenomenon known as zero voltage switching, in which we're going to look at this in our next class. So zero voltage switching is a concept, or is a type of is a very nice idea that was introduced, concept that was introduced so that it will cater for the switching losses along these points when we switch between the primary and the secondary side. Okay, so it allows for time delay and to allow for each switch to pick up. So when all the switch in the primary side are equals to 0, what happens is that the inductor current supplies the current, or ramps down by supplying some current along the circuit. Okay, and this current charges the capacitor or discharges the capacitor, and this phenomena is known as switching current. And while it do this, it will make the voltage across the switch either equals to 0 or equals to V1 on the primary side and V2 on the secondary side. In doing so, one capacitor will be fully charged and the other capacitor will be discharged. When the capacitor that is discharged reaches 0, it will forward bias the diode. That's when the diode conducts in this case. After the diode conducts, it paves the way forward for the switch to conduct. That's how the transition occurs in a DAB circuit. Thank you very much, and follow me in the next video to learn more about zero voltage switching.